Hi, everyone. Let's talk more about elements, atoms, and the periodic table. Okay, so let's explore these topics here. We're going to discuss atomic mass. There's actually two definitions you need to be aware of. We'll see Avogadro's number again as we describe atomic mass. There are families you need to know, families of elements. Specifically, there's names, family names, of the groups of atoms in a column. Not every column will have a family name that we need to know, but there are certain ones that will be quite useful to us. Next, we'll talk about where the electrons can be found in the atoms, and that's kind of a fuzzy topic, kind of captured in this theory called quantum mechanical model of the atom. And then, after we kind of get an idea where the atoms are supposed to be found, we'll record them, we'll report them as electronic configuration. Finally, there's a shortcut where we're going to just look at the electrons on the surfaces of atoms, the valence electrons, and use a little shortcut method called Lewis dot structures. And these short little drawings, notations of atoms and how many valence electrons they have on the surface, they'll be very useful to creating molecules. Molecules where we connect atoms to atoms to make new materials. Okay, let's go right to it. Let's talk about atomic mass. Okay, atomic mass. In a previous video, we talked about how there are different isotopes for elements. For example, hydrogen, the first element. Whoa, I forgot to edit this, sorry. That's a 2 here, and this is a 3. Okay, so there's 3 isotopes of hydrogen, and these are their chemical symbols, right? They're both, all 3 are hydrogen, and hydrogen is the atom that possesses one and only one proton in the nucleus, and that gives it particular properties that we know as hydrogen. Okay, however, sometimes there's an extra proton in the nucleus, and protons, did I say that right? Neutrons are found in the nucleus, and an extra proton, not an extra proton, a proton with a neutron will have double the mass of a single proton, right? So most of the hydrogen just seems to have only one proton in it, 99% of them on average. About 1% of the hydrogen we found on planet Earth has both a proton and a neutron. And in rare cases, we can find a hydrogen atom that's hydrogen with 1 proton and 2 neutrons. And then it has a mass number of 3. That combination of 2 neutrons, 1 proton is not stable. This is a radioactive element. So we're fortunate that there's not much around, but there is some around that exists. Okay, so then you say, well, on average, how much does a hydrogen atom weigh? Well, if you knew exactly which isotope you had, you could tell exactly what the mass is, right? So if you had the radioactive form of hydrogen, it has a mass of 3 atomic mass units. AMU for atomic mass unit. Got clever. Deuterium has a mass of 2. Deuterium is the second isotope, 1 proton, 1 neutron. However, if you have like 100 hydrogen atoms, you want to say, well, on average, how much does one of those weigh? Well, in the previous video, we did the calculation, and the average is 1.0079 atomic mass units. And that's because most of the hydrogen weighs just 1 mass unit, but every once in a while, there's a deuterium atom that weighs a little bit heavier. Take the average. It's not halfway between 1 and 2 because there's so many hydrogens that just have 1 proton that the average mass is 1.0079. Cool, okay, so that's the first definition of atomic mass. And if you're exploring single atoms, it's useful. But in the real world, you're talking about, well, let's go, let's weigh out a bunch of water and figure out its chemical formula, H2O, and, get some mass, do some calculations with that. You're gonna have lots and lots of atoms. And so now the atomic mass, this 1.0079 actually takes on a new value, a new meaning, and it's right here defined. The atomic mass is the weight in grams if you have Avogadro's number of atoms of that element. So that's kind of cool. Avogadro's number is this crazy number, crazy huge, 6.022 times 10 to the 23. So what that means is you start with a 6, and then if you just round off the one significant figure, follow it with 23 zeros. The US, oh yes, yeah. That's a huge number. But it turns out that's the number of hydrogen atoms you need, so that on the balance, if you could pile up 6.022 times 10 to the 23 hydrogen atoms on a balance, the balance will read 1.0079 grams. Not ANU, we're not talking about individual atoms. Now we're just taking a whole collection, huge number of atoms. Cool. It's actually more useful in the reverse direction. We'll take some atoms of hydrogen, start piling them onto a balance, and stop when the balance reads 1.0079 grams. And automatically, you know you must have Avogadro's number of hydrogen atoms. Very cool. What's my periodic table? Let's go right here. Cool. And we'll zoom in. Doesn't work just for hydrogen, but all the other elements as well. Sorry, the resolution is kind of poor. I don't know how well you can see this, but here's uranium, and the atomic weight or atomic mass is 238.0289. 238.0289 grams. So if you pile up, uranium is a really heavy metal, and you put a bunch of these pieces of uranium onto balance, and you stop adding uranium, little blocks of this metal, when the balance reads 238.0289 grams, on the balance will be 6.022 times 10 to the 23rd atoms of uranium. So you can count atoms by weighing them out. That's cool. Okay, we're going to find that really helpful when we start looking at chemical reactions. And I think of chemical reactions sort of like a recipe. If you're trying to make a cake or make some cookies, right? You need to add the ingredients in the right proportions, the right amounts. And if you add too much of one ingredient, it messes up the recipe. Chemical reactions are the same thing. If you want to do a proper chemical reaction, you need to add your reagents, your atoms, in the right amounts. And so we need to count them. We need to measure them out. And this trick with atomic mass will be our way of trying to count those atoms. Just weigh them, get to the atomic mass, and you'll know you have Avogadro's number. Avogadro's this, Avogadro's that. We get tired of saying Avogadro's number. Sure, we give him a little homage. Good job, Avogadro, figuring this out. But you know what? I'm tired of saying Avogadro every time I need to talk about this collection of atoms. So the nickname for Avogadro's number is mole. I know, it comes from the abbreviation of molecule, which is not a good origin name. Sorry, it gets a little confusing. And there's also that little rodent in the ground that's a mole. Nah, not that guy. So think of mole as meaning 6.022 times 10 to the 23rd. Think of it just like when you hear the word dozen, you should be thinking 12. So if I say a mole, you should think of Avogadro's number, 6.022 times 10 to the 23rd. I know, that crazy number. This is also another case for why you need to use a scientific calculator and no scientific notation, because there's not many calculators that allow you to hit a 6 and then 23 zeros and still display that number on the screen. Yeah, you definitely have to be comfortable with scientific notation. Exponential notation, if you will. All right, enough about atomic mass. Let's look at the periodic table. Okay. So there's some things you need to know. You always get, first thing, you always get a periodic table in my exams. You just need to be able to use it. So you don't have to memorize the periodic table. It'll be provided. But you need to know how you can get useful information off of it. So here are some key ideas, key concepts, if you will. Okay, what do we need to know about the elements and the periodic table? Well, first of all, most of those elements are metals. Some you're familiar with. So we go over here to the bottom right of the screen. We got Cu, which is copper. Below that is silver. Underneath that is gold. Oh yeah, you've heard of those, and they're all metals. There's nickel and iron and chromium, titanium. Maybe you've heard of that. Sodium. That's weird. I thought sodium was found in salt. Salt's not metallic. That's true. Salt is not metallic, but pure sodium is a metal. Kind of weird. So anyways, most of the elements are metals, but not all of them. So if they're not metals, got the nice scientific term, non-metals, okay? Hydrogen, not a metal. So over here is copper, that's carbon. Carbon comes in a couple different forms. Diamond, one form, that's not a metal. And charcoal, graphite, one of the materials found in pencil lead. Yeah, that's not metallic. Carbon's not a metal. How about oxygen? No, that's a gas. And even if you could cool it down and freeze it out, make it a solid, it's not a metal. Helium? No. Okay, so those are some examples of non-metals. And what's really cool is that if you just look at this diagonal line, so I made this much more bold, much more visible on my periodic tables that I will provide for you on your exams. So at a glance, this diagonal staircase is your dividing line between the metals on the left and the non-metals on the right. So if I say, okay, boron, what is that, metal or non-metal? You'd say, okay, boron is on the upper right side of that staircase. It's a non-metal. So is silicon, so is phosphorus, so is argon, boron, bromine, Br. The one exception, and darn it, chemistry is full of exceptions, hydrogen. Hydrogen should have been over here on the right side. Some old periodic tables do list hydrogen on this side. Get all the non-metals together. Our periodic table physically detaches hydrogen. It's kind of floating up above lithium here. That's a nice visual sign to say, wait, it's not really supposed to be over here if we're looking at metals versus non-metals. Hydrogen's a non-metal. But for other reasons, it's better to think of hydrogen as belonging to this column. Not really. We'll get to that in just a second. More about just big terms. Silicon, you may know that you heard of Silicon Valley, computer chips. Computers run on electricity. Metals are conductors. Why is silicon not a metal? It's a non-metal. Well, you know, nature isn't all yes and no, one side or the other. It's kind of blurred. Silicon's actually a material that's in between a metal and a non-metal. Now on an exam, I say, hey, silicon, is it a metal or a non-metal? I'm forcing you to make a choice. You should say non-metal. It's more like a non-metal than a metal. However, in real life, silicon has some properties like a metal, some properties like a non-metal. The term for that is metalloid or a semiconductor. Okay, that's not so important for the chemistry we are going to discuss in this class, but it's out there. Again, if I say, okay, arsenic, metal or non-metal, you'd say, okay, arsenic is a metalloid, Dennis. I said, I didn't ask that. Metal or non-metal? You got two choices. Arsenic then is on the upper right, non-metal. And antimony, right here, antimony is on the bottom left. That's a metal. That's how we'll answer. And we're going to use that concept of metal and non-metals much later in this course. It'll be helpful. And if you say it's a semiconductor, it's going to be difficult to use that information in the context of later in the semester. Cool. Okay. Metals and non-metals. Got it. Diagonal line. Next key concept is this, that elements in the same column have similar properties. Kind of hinted at that earlier when we looked at this column, copper, silver, gold. I mean, they're great at making wires and jewelry, and they're really durable. They don't tend to corrode so much. Well, exceptions, right? Silver. Actually, copper has a little oxide coating on it too. But these have similar properties. And that's the general trend on the periodic table. If you look at a particular column, those elements found in the same column tend to have similar properties. So if you know something about copper, you can predict what gold is going to do. And when element, I think at this time, element 111 has been made artificially, we should be able to predict some properties of this new metal. It should have properties similar to gold, silver, and copper. Cool. So that's a valuable thing to know. And so it turns out that this trend, that elements in the same column have similar properties, we call that a column a group or a family. And then a family is going to have a common last name. So I need you to know 5 family names. And here they are. So column 1 are the alkali metals. And it begins with lithium. Here's column 1. Lithium, sodium, potassium, rubidium, cesium, francium or francium, however you want to pronounce it. Hydrogen's really not in that family. It's not a metal. And the family name is alkali metals. Hydrogen is just kind of the exception here. So if on exam I say, give an example of an alkali metal, you can pick any one of these. Yeah, cool. Column 2, alkaline earth metals, beryllium, magnesium, and so on. Then it gets a little goofy. Instead of looking at one column, there's a whole metal block here. So from scandium all the way over to zinc and down, cadmium, mercury, this middle block, those are the transition metals. That's their family. So on exam, I say, tell me, give an example of transition metals. Go for this middle block. There's plenty of transition metals there. Okay, so there are family names for the other columns, but they're not used that frequently. But the next to last column right here is used quite frequently. These are the halides or the halogens. You may have heard of halogen halides. So that's pretty common. So you'll need to know that fluorine, bromine, iodide, the last one here, there is radioactive. I'm not really going to use that one, but this column contains the halides or the halogens. And finally, the last column are the noble gases. So 5 family names. Yes, I need you to memorize those. It's going to be useful to us. Okay, noble gases. Why such a regal and royal name? Well, noble gases are actually quite special. They don't react. They're really stable. And it turns out, why is that? Well, they have special numbers of electrons. You might think of them as magic numbers of electrons that make the atom really stable. First of all, let's just get these main ideas in check here. When we say it doesn't react, that's the same thing as saying something's really stable. If something is not stable, then it's going to react. That's pretty straightforward. Kind of works with people too. Your best friend, you can tell them anything. They're really stable. They'll listen. They'll console you and stuff. But be careful about that person over there. Ooh, they're really reactive. Say the wrong thing and they'll set them off. Right? So very reactive person versus very stable friendship. Very stable person. Cool. What else we need to know? Okay, so you'll get the periodic table. You'll be able to figure out what those special numbers of electrons are. Right now, I just want you to know that's a pattern of the elements, is that the last column of elements are the noble gases. They're noble because they don't react. Why don't they react? They got nature's favorite numbers of electrons. Something's magical, special, stabilizing. And it turns out the rest of the elements on the periodic table are jealous, and they are going to react in order to try to achieve one of those special numbers of electrons. So that's going to be really powerful for us. So in the next couple of units, we're going to look at chemical reactions. We're going to have to predict how things are going to turn out. And this will be a guiding principle for us. If you look at the periodic table, and let's just look at, I don't know, fluorine maybe. And I might have a question on exams like, oh, fluorine's doing a reaction. Predict the products. What? Okay, so the idea would be this. Here's fluorine, element number 9. It's one of the halogens. Okay, that's not so useful here, but it's interesting. Fluorine, what are you going to do? Well, it's not a noble gas. It's not stable. It wants to try to get to a magic number, a very stable number, one of these special numbers. What are they? Well, remember, atoms are made of atoms. Sorry, atoms are made of electrons and protons, and nature likes stable, balanced things. So in a stable helium atom, there's going to be, well, helium is element number 2, so it has atomic number 2, which means 2 protons. And so to balance that, helium is going to have 2 electrons. So 2 is a magic number of electrons. Neon right below it is element 10, 10 protons, that's the atomic number. Yeah, but in a neutral, stable neon atom, there are also 10 electrons. Argon has 18 electrons. So fluorine comes in with 9 protons. Nature gives it 9 electrons, and fluorine's not happy. The magic number is 8, 10, and 18. The closest one is 10. So fluorine's chemistry, its reactivity, is governed by the fact that it wants to steal 1 electron or borrow or share 1 electron. That's its chemistry. That's its reactivity. All about trying to get the special numbers of electrons. Cool. Anyways, that's going to be helpful to us. Right now, just know the names of these families. Alkali metals, alkaline earth metals, transition metals, that's a big block in the middle. The halogens or the halides, and finally the noble gases. And realize the noble gases are noble because they have those special numbers of electrons. Oh, just to avoid some problems on future exams. Suppose I say, hey, what family does sulfur belong to? What family does sulfur belong to? And someone says, oh, it's a non-metal. You don't get any points. Non-metal is not a family name. Yes, sulfur is a non-metal. That's just something it does. It has its property. But sulfur, sulfur has a different family name, which I didn't give to you. So that was a bad example. No problem. Bromine. Bromine. What's the family name for bromine? That one could be on the exam. And you can't say non-metal. It is a non-metal, but that's not the family name. It's a halide or halogen. I think the oxygen family group's like chalcogens or something like that. Chalcogens, I forget. I don't even use it, so I don't know. Okay, but just remember on exams, metals, non-metals, metalloid, they're not family names. Don't use those on a question asking you for one of the group names, column names, family names. Okay, that's it. What's next? Go to the top of the next page, that's what's next. Electron configuration and the quantum mechanical model of the atom. Where are those electrons? Okay, let's start with our understanding of atoms that began with protons and neutrons in the middle in the nucleus. And the electrons are zipping by, they're in motion, flying around in orbits, if you will, they're all around. Okay, a little bit more description, a little more detail. Those electrons are kind of arranged in the shells. And so it's not like a hard surface like this, but you gotta get the idea that if you were watching, you could see the electrons in flight about the atom circling round and round and round it goes, not on a circle, but more three-dimensional. Then you might say, hey, I'm watching some of these electrons, and they're staying pretty close. They tend to hang out in this volume of space, and we'll call that the first shell. And there's some other electrons. You watch them for a while, watch their flight patterns zipping along here where they're hanging out, and they're in this region that we'll call the second shell. And then there's other electrons that tend to be on the surface. They're the ones that are farthest away from the nucleus. Sometimes they dive in, they come back out, and they're flying all around. But on average, they seem to be on the surface of this atom, the third shell. Okay, so that's how electrons tend to be arranged in atoms in these shells. And the farther away they are from the nucleus, the more energy they must have. So if they're moving pretty slowly, I kind of think of that. It's like, well, then they're hovering really close to the nucleus, like in the first shell. But if they have a ton of energy, a lot of motion, woo, there we go. They're way out, maybe in the 15th shell or something, right? So they're going to be farther away, have a lot more energy. And if you pump in enough energy, we saw in the previous video, the electrons can absorb light and acquire more energy to go to higher shells. Well, it's possible you could shine enough light, a light of enough intensity, not intensity, sorry, enough energy, light with enough energy, so the electron could absorb that energy and actually escape the atom and fly away. I kind of remember that. That helps me remember as you look at electrons farther away, they're actually more energetic. They have higher energy. Okay, and I kind of already said a couple of times, kind of a key concept here. Valence electrons are on the surface. They're in the outermost shell. And if you want a name for all the other electrons, they're in the middle, like an apple core is in the middle. The core electrons are just all the other electrons. Cool. Then this is where it gets a little fuzzy, a little weird. Turns out that electrons within shells, within an atom, they only can have certain amounts of energy. I find that hard to understand, especially if I think of electrons zipping along with some speed. Like maybe the electrons in the first shell are going 50 miles an hour, electrons in the second shell are going 100. Shine some light on those slower electrons, make them go faster, so they go from 50 to 100 instantaneously. All our experiments are saying that those electrons can never have any value between 50 and 100 miles per hour. Wait, how'd you go from 50 to 100 then? Didn't you pass through 75? Sorry, all our experiments, all the data suggesting no, it was 50 miles an hour 1 second, next second after absorbing the light, next instant, shorter than a second, it's at 100, just bounces right up there. They only have certain amounts of energy. That's the definition of quantized, is where you only have fixed amounts. And in the real world, we do have some things that are quantized. Stairs are quantized. So how are stairs quantized? Well, think of this, the first step, here's the second step, the third step, and the fourth step. And I say, hey, go stand on the 2.5 step. And in our universe, you can't do that. You can't just hover halfway between step 2 and 3. No, you're either on step 2 or you're on step 3. You can only have one of two values. If I say go 2.5, impossible. You're on 2 or you're on 3, that's it. That's as close as you can get to 2.5. It doesn't exist. And that's the same for electrons inside atoms. There are certain amounts of energy, and there are just others that are just forbidden. Can't be at that energy. Oh, by the way, before I forget, 50 miles an hour, I don't know what the speed of electrons are. They're very, very fast. And if you take more chemistry, more physics specifically, you'll discover that electrons behave more like waves than particles inside atoms. So there's that. Again, quantum mechanics, interesting topic. Right now we're just getting the highlights so we can understand chemistry. Okay, so we got valence electrons, core electrons, electrons in shells, and they have discrete values of energy. They're quantized. Can't just have any. Okay, that's where we're at now. Let's dive in a little deeper. Okay, within a shell, if you watch those electrons and look at their flight patterns, the shells seem to be divided up into subshells. So let's go back to shells. We have the first shell, the second shell, the third shell. We're labeling the shells with numbers. As you look within a shell, watching those electrons and their flight patterns, the way they orbit, if you will, the nucleus, there's some differences. We're going to label those differences, these subshells, by letters. There's an S, a P, a D, and an F. A little history, why are these weird letters? Why isn't it just A, B, C, D? Comes from S is sharp, P is principal, D is diffuse, F is fundamental. Yeah, the history here. the data we obtain from electrons comes from absorbing and emitting light. And so we took some, scientists took pictures and they saw some sharp lines, some principal lines, some diffuse images and some fundamental images. And that's what they labeled those lines, those, I keep saying lines, just, different colors, if you will. That's the origin of those. And they stuck. And it turns out these 4 subshells are the most common ones, the ones we're going to deal with. But if you give electrons higher and higher energies, go to higher and higher shells. Think of shells sort of like parking lots or flight patterns. So this atom, this picture of an atom up here has 3 shells. That's where the electrons are. The atom ran out of electrons. There's no more electrons to put in the 4th shell. There's no more electrons to put in the 5th or the 23rd or the 170th shell. But a shell is just a region of space. So it's there, it exists. If you had some more electrons and they had enough energy, they could go to the 253rd shell. It's just a region of space. It's out there. So you could talk about that shell. And then you could talk about subshells. And the bigger the the bigger the shell, the more ways you can cut it up. So the 3rd shell, you can cut up into S, P, and D subshells. When you get to the 4th shell, it's bigger. So you can cut up the 4th shell into an S, P, D, and an F. When you get to the 5th subshell, you can actually cut it into an S, P, D, F, and then another subshell. And after that, it just goes alphabetical order. G, H, I, J, K, L, M. Yeah. That's the procedure. But again, S, P, D, and F as far as we go. And finally, within the subshells, you can actually talk about orbitals. So here we go. I'm visual. This is going to help many of you who are also visual learners. If you look at the 3rd shell, the 3rd shell can be broken up into the S subshell. And what does that look like? Well, that looks like a sphere, a ball. The nucleus is at the center here. And the electron that is in the third shell and the S subshell of the 3rd shell, we'll just abbreviate that, the 3S subshell. That's going to be the electron's going to be flying around here anywhere in this volume of a ball, volume of a sphere. That's the S subshell, excuse me. It's also the S orbital. We'll come back to that in a second. The P is another subshell within the 3rd, and it looks like a 3-dimensional figure 8. So if you're watching an electron, it's dancing back and forth, or maybe it hangs out over here and it comes over here and back and forth it goes. That's its flight pattern. It's a p orbital that goes in and out along this x-axis. Another flight pattern is this electron that's doing the figure 8 dance 3-dimensionally that goes in and out along the y. And then there's also an up-down figure 8 pattern. That's a p subshell too. The orientation differs. So it turns out within the 3rd shell, there are p subshells, and it turns out there's 3 of them. Along the x, along the y, along the z, the up down, the in out, the left right, subshells are p. And then there's the s. And it turns out there's only one form of the s. So this is one orbital, where the electron can be found. And here's another orbital where the electron can be found. Another orbital, another orbital. And then within the 3rd shell, you can also split it up into 5 pieces called D subshells. And they look like 4-leaf clovers, except for this weird one here. It has a donut around the figure 8 dance. Okay, I'm not asking you to memorize these. Well, maybe not this one. You should know, maybe I am. It's actually quite helpful when we look at how atoms connect to other atoms. We'll see later in the course. And if you take more general chemistry, you'll explore this more deeply. So you should know, I take that back. You should know that the S is a sphere and S stands for sphere. I know, originally it stands for shark, but sphere is a better connection. P is like the dumbbell, the figure 8. And then D is a 4-leaf clover. And you can orient that 4-leaf clover in lots of different ways. That'd be fun, I think, to watch an electron doing the the 3D dance, right? So it's doing a figure 8 and then it kind of jigs over here and does a figure 8 this way and back and forth, or hangs out here, there. And that's its flight pattern, just hanging out within these regions of space. This whole 4 groups here constitutes one flight pattern, one orbital, the 3D orbital. Cool. Okay, what do you need to know? That's quite a bit. Know the general shapes, S, P, and D. Okay, so now we kind of know where electrons can be found. As we look at a specific element, we will use the periodic table to map out where all the electrons are. Okay, so a little background before we get to actually specifying exactly which orbitals contain those electrons. We need to know a little bit about how nature builds up an atom. So I imagine she starts with protons and neutrons in the nucleus. And she says, well, what do I want to make today? Maybe I want to make a gold atom. So I need 79 protons. Okay. Go to the periodic table. Element 79 is gold. And then she starts adding some electrons one at a time. And they start flying around those 79 protons with some number of neutrons. Nature will decide how many neutrons does it take to make a stable gold atom. Okay, so where do those electrons go as they are added to this growing atom that's going to be a gold atom? Well, the off-bow principle states that the electrons will go to the lowest energies first. So orbitals, regions of space, will fill from the lowest to highest energy. So as you throw in an electron, it goes to the first shell, the lowest energy state, right? Because as you go to higher shells, higher energy. Cool. Where does electron number 2 go? Well, that's Hund's rule. Hund's rule says when you start filling up orbitals of equal energy, spread out the electrons. Electrons repel, so spread them out. So we saw up above that there's an S subshell, and then there's some P's. So it turns out the P orbitals generally have the same amount of energy. So if you start filling P orbitals, instead of putting 2 electrons in one of the P's, put 1 electron in each of the 2 P's. And then if you add a 3rd electron, put it in the other P. And eventually if you put in 4 electrons, well now put a 2nd electron, pair up electrons in one of the other P's. We'll go ahead and get into that in a little more detail in a second. We're just getting the general rules of the game. Off-bow principle states, put electrons in the lowest orbitals first. Hund's rule says if you have more than one choice at your particular energy level, spread out the electrons, put an electron into each orbital before you pair them up. The Pauli exclusion principle says 2 electrons maximum per orbital. So once each orbital has 2 electrons, you're done. Move up to the next subshell. After all the subshells are filled, move to the next shell. And our shortcut, the way we're going to map out where those electrons are, we're going to use the periodic table. It's going to configure the atom with the proper number of electrons and the proper flight patterns. Cool. And out of this is coming the main idea that as nature builds up atoms according to these 3 rules, the last electrons will be on the surface, the valence electrons, and it's going to have the same pattern for a family. Family of elements has the same number of valence electrons. So over here I got this fun little map. If we look at the halides, fluorine and chlorine, fluorine has 9 electrons, 9 protons. Fluorine has 17, that's kind of weird, but the way the electrons go into shells is such that, let's look at fluorine. The first shell has 2 electrons. The second shell has 7. Chlorine, first shell has 2 electrons. Second shell has 8. Third shell has 7. Wait, fluorine's last shell had 7. Chlorine's last shell has 7. 7 electrons on a surface behaves much differently than 6 electrons on the surface, or 8 electrons on the surface, or 3 electrons on the surface. So the surface of the atoms, the valence electrons are going to determine the chemistry of the element. And elements in the same column have the same numbers of electrons on their surfaces, same number of valence electrons. Okay, let's get to the nitty gritty. Where are all those electrons? Okay, this is how we're going to use the periodic table. Here's the details. First of all, the objective is every electron has to be identified by which shell it's in. It's going to be identified with the number, first shell, second shell, third shell, fourth. You also have to say which shell number it's in. The choices are S, P, D, and F. Shell number doesn't sound very scientific. Scientists come along and say, we need to make that more sciencey. So the shell number is called the principal quantum number. It turns out, if you're using the periodic table, it usually corresponds to the row number. So hydrogen, here's a periodic table down the bottom of the screen. Hydrogen and helium are in the first row. Hydrogen is 1 proton, 1 electron. Hey, electron, which shell are you in? Well, off-bout principle says it goes to the lowest shell, the first shell. Hey, this is row 1, which corresponds to the first shell. Cool. And then, we'll see if there's exceptions. Darn it, chemistry. You have these nice little patterns, but the exceptions to the pattern. When we get to the transition metals, wait, the who, the what? Transition metals are the middle block elements here, right? So then again, we're gonna need little family names. When you're looking at the last electron to go into, let's say, iron, right here, you're in the you're in the 4th row. So I would have thought the last electron should be going to the 4th shell. Well, there, nature, she makes the rules. Says no, the last electron is actually in the 3rd shell for iron. So we're gonna have to remember that, yes, most of the time as you're going across and looking at the row number, that's your shell that the electrons are going into, except when you're in the transition metals. In this middle block, you're actually filling a shell 1 less. There it is, right up here. 1 less than your row number. So iron's last electron is going not into the 4th row, 4th shell. No, it's actually filling the 3rd shell. And then if you're looking at these elements down here, well, where are these? Well, this cerium is element 58. Where's 56? Right here. 56 was row 6. 57, row 6. 72, wait, 57 and then 72. What's going on here? Oh yeah, so once you get element 57 taken care of, you jump over here and do 58 through 71. So I kind of think of the lanthanines, that's the name for this. You don't have to memorize that. But this row of elements is actually part of the 6th row here. But when you're looking at the last electron into these elements, and I think, wait, aren't they in row 6? Aren't they filling the 6th shell? They're actually filling the 4th shell. So these elements are off the table at the bottom. Find out where they are and go 2 shells less to identify their principal quantum number, the shell number. It's going to be 2 less. Okay, we'll get some practice with those in just a second. Principal quantum number is the shell number. Subshell letter, well, the sciencey term for that is the angular momentum quantum number. And then to get that from the periodic table, identify your columns. So it turns out that alkali metals and alkaline earth metals, the last electron is going into the S subshell, the one that looks like a sphere. The last electrons for the transition metals, they're going into the D, the 4-leaf clover-like subshell. These 4 columns, the last electron is going into the figure 8 subshell, the P subshell. And then these 2 rows off of the bottom here, these are filling the F subshell. Oh my goodness. So electron configuration involves reporting the shell number and the subshell letter, and you use the periodic table. Basically, the row number gives you the shell number, and its location column-wise gives you the letter, the subshell letter. Very clever. Now, if you take more chemistry, you're going to find some exceptions to this. We're not going to cover those crazy exceptions today. We'll wait for you to take general chemistry and explore this in more detail. But just as a warning, this quick little pattern breaks down in some places. Let's try this out. Let's see. Let me check the list. Make sure I didn't forget anything. Nope. Nothing more. Good. Let's give it a go. How does this work? Clean periodic table. Start up here. Let's give myself some room. Let's start with the basics and say, okay, what's the electron configuration of helium? Okay, so that's He. So I guess I should start the basics, right? So on the exam, if I say give the electron configuration of helium, electronic configuration of helium, search periodic table for the word helium. Here it is, element 2. Okay, helium has atomic number 2, which means 2 protons. But we're going to assume it's got an equal number of electrons. It's neutral, so it's 2 electrons. Where are those 2 electrons? Okay, well, where's the first electron? Off-bow principle says it goes into the first shell. Well, that's row 1. So we're going to write a 1 here. The first electron is going to the first shell, 1. What subshell? Well, the electron goes in where hydrogen's electron is. So hydrogen is in kind of above column 1 here, the S block. So the first electron in helium is configured the same as hydrogen's first electron. It's one and only electron. First row, S block. Cool. Pauli exclusion principle. Okay, all these rules. So fill the lowest one first. That's off bow. If you have more than one orbital, spread them out one at a time. Pauli exclusion says 2 electrons maximum. Okay, so we just put 1 electron into the 1s orbital. That orbital can hold 2. So helium's second electron is going to fill the 1s. And we're done. And I know helium's over here in the p block. Sorry, I guess there's an exception. You need to finish filling the orbital before you can move up to the next subshell or the next shell. We're done. So on exam, if I say what's electron configuration helium, you could say it's 1s squared. The little 2 to the second, this little superscript 2 just means, hey, the s electron, the 1s orbital, the 1s orbital has 2 electrons in it. Or you can use lines and say, hey, there is an orbital, the 1s orbital, and I'm going to put 1 electron in here and use a little half arrow to show that. And the second electron is going to be an upside down arrow. I didn't want to get too much into detail in the quantum mechanics here, but I think this is important enough I should digress a little. Electrons have magnetic fields associated with them. Electrons can behave like them. Okay, so here's a question I grappled with as a student. Wait, I thought electrons repel electrons. How come you got 2 electrons into an orbital? Don't they just repel each other and get out of that common flight pattern, that common orbital? Yes and no. The electronics, electric repulsion, electrostatic repulsion, is trying to repel those 2 electrons away from each other. But if one of the electrons has north pole up, the up arrow, and the other electron has north pole down, magnetically, they can attract each other. There's something called pairing energy. You still have to get these electrons close together. So electrons repel electrons electrically, but magnetically, they're starting to attract each other. Nature, she makes all the rules. You can get 2 electrons in here, and one way they explain why is magnetically. They attract each other. This magnetism is called spin. Okay, enough with that. Bottom line is my class on most exams in other classes around the world in general chemistry, electron configuration can be written as 1s squared for helium, or you can draw a line, put two arrows, one up, one down, and write 1s underneath. We have now configured the electrons of helium. 2 electrons in a 1s orbital. Let's do boron. Electron configuration of boron. Well, here's the word boron. There's the symbol B. It's element number 5. There's 5 electrons in there. So where are those 5 electrons? Well, the first 2 are configured just like helium's first 2. Well, helium's only 2. First electron behaves like the electron in hydrogen, which is row 1, s block. So I'll write 1s, or I'll write 1s with the arrow up. The second electron fills out this orbital, arrow down, or 2. Up here's 2 squared. Took care of 2 electrons, but there's 5 altogether. So where's the third electron? It's configured the way lithium's third electron is configured. Lithium is found in the second row. Ooh, so now we're in the second shell. Which subshell? Columns 1 and 2 constitute the S block. This block of elements are S. Lithium is in the third electron, last electron of lithium's in the second row. It's in the S block. 1 electron here, the third electron, 1s. This is the electron configuration for lithium. 1s squared, 2s. You could put a 1 here if you wanted to. Or, you know, anytime you have a variable by itself, it's understood it's to the first power. So you don't have to put a 1 there. If you like the arrows, I can count 3 arrows. That's cool. 3 electrons. This is lithium's electron configuration. Wait, we're doing boron. So where's the 4th electron? Well, the 4th electron is configured like beryllium's. 4th electron, second row, S block. Second row, S block. Wait, that's just filling up this orbital. Where's the 5th electron? Well, here's boron. Its last and final electron is here in the second row. But now we're in the P block. That's supposed to be a bracket. So we're in the second row, second shell, P block of the second shell. P is a subblock, right? Put 1 electron in there. If you want to put a 1 there, we're done. We have 2 plus 2 is 3. 2 plus 2 is 4. My goodness. And 1 more is 5. 2 plus 2 is 4, and 1 more is 5. We have all 5 electrons of boron. Here's the electron configuration. You can do it either way on the exam, or I might specify, show that little half arrow form of electron configuration. So you need to be able to do both. Cool. All right. Let's do titanium. Titanium. So you look on the periodic table, if you find the word titanium, it's right here. It's element 22. 22 electrons to configure. But you see the pattern already. We already did boron. So the first 5 electrons of titanium are configured just like boron's 5 electrons. So what was it? Well, start with hydrogen. First row, S block. That's S. Or you with the line, 1s, this first electron. 2 electrons are needed to fill that subshell. Where's the third electron? Well, here's element number 3. It's in the second row. It's also in the S block. And the S block is 2 elements wide because 2 electrons will fill the S subshell. And we've taken care of the first 4 electrons of titanium. Okay. 5th electron starts filling the P block. Let's go back to our pictures of the subshells. Yeah, so it turns out when you're in the third shell, there's 3 P's. And actually, anytime you have a P subshell, there's going to be 3 of them. When you're filling D subshells, there's going to be 5 of them. S has only 1. Wait, 1, then 3, then 5. 1. So S, P, D, F. 1. There's 3 P's. There are 5 D's. What do you think F is going to be? 7. Another odd number. 1 to 3 to 5 to 7. How many little lobes do you think it's going to be in the F subshell? I got 1 thing here, I got 2 here, I got 4 here. This one's going to be 8. I'm not going to ask you to look at the 8 leaves of a clover F subshell, but anyways, that's what it is. You don't have to memorize that there's 3 P's. You don't, because you got the periodic table. So what's the pattern here? Well, to fill the S was 2 columns wide. It took 2 electrons. The P block is 6 atoms or elements wide, 6 columns wide. So I got 2P, but I want to get 6 electrons here to fill the P block. But each orbital has a maximum of 2. So that gives me 3 P's, right? P's, there's the PX, the PY, the PZ. We need to fill the P block. Every line is an orbital, and Pauli exclusion principle says 2 electrons per orbital. All righty. Element number 5 has the 5th electron in the P block, second row, P block. Good. Put in that 5th electron right there. Carbon holds the 6th electron. It's also in the second row, P block. I don't pair it up. Hahn's rule says, hey, we have these 3 orbitals all equal energy. Why are you squeezing these 2 electrically charged, negatively charged electrons together so they can repel? No, spread them out. That's better. Nitrogen is holding the 7th electron. It's in the second row, P block. So put the next electron in its own orbital, spread them out. Hahn's rule said, spread them out. 1 electron into each orbital when orbitals have equal energy. Where's the 8th electron go? Well, it's still second row P block. Well, now I have to pair it up. So I might as well go back over here and say, okay, electron number 8, you're going here, pairing up, and your spin is opposite magnetic field. 9th electron, right? Because we gotta get to 22 for titanium. It's gonna pair up here. 10th electron. Wait, 10th electron just ended row 2. We just filled the second shell. We're at a magic number of electrons. Neon has a completely filled first and second shell. Nice and full, complete, nice and stable atom. Neon is noble. Oh wait, we're doing titanium. Okay, electron number 11 is found on the 3rd row back in the S block. Ooh, so 3rd row is S, it's back in the S. 3rd row is 3, we're in the S block. I forgot to make a notation as to how many electrons are 2P. Well, there's 2, 4, 6. Now I'm filling the 3S subshell, and it's 2 columns wide. Electrons number 11 and 12 go into the 3s orbital. Where's the 13th electron? Well, aluminum is the 13th atom. It's in the 3rd row, P block again. 3rd row, P block, and there are 3 P's. 3P. Electron 13, 14, 15 spread out their electrons into each of the 3p orbitals. Electron 16, 17, 18. It's going to pair up all the 3p electrons. We just filled the p block on the third row with 6 electrons. Titanium is 22, and we got 18 total. We just made argon. This is argon's electron configuration. 19th electrons back in the s block, third row. That is not third row. This is fourth row. 4s. We're in the s block, fourth row. We're in the s block, fourth row. 4s electron. Electron 19 and 20. Fill the s orbital on the fourth shell. Titanium, I see you. You're 2 electrons away. Okay, electron number 21 is element 21 is one of the transition metals. We are now in the D block. In the fourth row of the D block, but this is our exception. The D block, the shell rather, is in 1 shell number lower. So I know I'm in the fourth row, but my shell number is 3. And I'm in the D block. So just remember that transition metals are the D block, they're filling 1 shell lower. Okay, and how many D orbitals are there? Well, you can go back and look at the pictures of those clovers. There were 5 of them. Or you can say, okay, there's the S has 1, the P's have 3, and the D's have 5. Okay, so scantium, element 21, your 21st electron went into the D block of the third shell. Titanium, there you are, your 22nd electron. Your last electron is also fourth row, wait, that's a D block, this is 3D. And Hund's rule said spread them out. And that's it. There are 2 electrons in 3D orbitals. We just finished electron configuration of titanium. Cool. And then so the pattern just continues on as you fill and fill more and more elements. On exams, I won't have you fill more than a D, but maybe in the homework it might ask you to go beyond filling the D block. So just know that once you get to element 57 and higher, you have to jump out of the main periodic table and go down here to these rows. Just follow the atomic number, right? So if I said, what's the electron configuration? The last electron of neodymium, element 60. Where is that 60th electron? Well, the 57th electron was here in the 6th row, D block, right? That's one 57, element 57 is a transition metal. The D block is filling the 1 row number below, right? So electron 57 is going into the, not 6, but the 5th D, so 5D. And there's 5 of those. So the 57th electron went there, but the 58th, I'll put a little 1 here to emphasize that, the 58th electron went over here. It came from the 6th row, but now I am in the F block. These 2 rows are F block, and they're 2 row numbers lower. So a minus 2 row number. So I was in the 6th row, but the F block begins with a 4. So the 4th shell is the first shell that can hold F subshells. And if D had 5 of these, the F has 7. 7. This is 4F. Whoops. Okay, so electron 58, we would predict, goes into the 4F subshell. Electron 59 doesn't pair up, spread them out. I'm in the F block. Electron 60, that's what I was asking. What's the 60th electron? It's in the F block with 4F, and it's unpaired. It's all by itself because we're going to spread them out among the 4F orbitals. What do you think? Whew. A lot of detail there. So rewind it when you need it. Let's get started on the homework. Actually, there's still one more topic left, Lewis dot structures. But when you get started on the homework, we'll do, go back and look at, Lewis dot structures, or go back to electron configuration or atomic mass, and then fast forward the video to what you need. So when it's time to find electron configuration, replay this part of the video, and hopefully that'll be helpful. Otherwise, jump on the discussion, ask your question, and get some help from your classmates. I'll try and get on the discussion board too and answer your questions, or just send me an email directly. But check it out with your classmates. I think if we have a good discussion there, it's going to help a lot more people than just you and I exchanging email. But, get started. Please contact me. All righty. I think we got all the subshells. Let's tackle the last topic, I believe. Yeah, Lewis dot structures. Okay, so we went through all the detail, tracking all of those electrons, putting down their configurations, right? So neodymium had 60 electrons. We could map out all 60 electrons if we needed to. But really, we're going to ask about neodymium's chemistry. So take a neodymium atom and bump it into some other atom, make them react. In order to react, the atoms actually have to touch, they have to collide. And which electrons are going to be in that first contact with the other atom? The electrons on the surface or the electrons in the core? On the surface, really. So all you have to do is know something about the valence electrons, the electrons on the surface. So when we start looking at chemical reactions, we're going to use Lewis dot structures to help us track those valence electrons. And we're going to use the periodic table too. So on your periodic table, the groups, the columns, have numbers. There's 1A, 2A, 3A, 4A, all the way up to 8A. The number in front of the A is the number of valence electrons for that family. So the halides, the halogens, are all atoms with 7 electrons on their surface. The valence number is 7. The alkaline earth elements, column 2A, 2A, yeah, because all these elements in this family, alkaline earth metal, have 2 electrons on their surface. There you go. Okay. We could identify the subshells and row numbers, the principal quantum number and all that, but a faster way to get through the chemistry part, the chemical reaction part, is drawing a Lewis dot structure. So what you do is simply go grab the chemical symbol for the atom you're talking about. So if you're talking about titanium, it's Ti. Lithium is Li, right? So use the periodic table to get its chemical symbol. And then we're going to represent the electrons, the valence electrons, using dot. Each dot means 1 electron. And follow Han's rule. As you start adding more valence electrons, don't pair them up immediately. Spread them out. And on a Lewis dot structure, the places where you can put dots, where you can put electrons, are left and right and up and down. So let's draw the Lewis dot structure for lithium. Okay, so I already did step 1. What's the chemical symbol for lithium? Li. Over here on the right. It's the 3rd element from the periodic table. Ooh, and knowing that it's the 3rd element tells us there's 3 electrons in the whole lithium atom. But Lewis dot structures just worries about the valence electrons, electrons on the surface. Lithium is in column 1A. There's only 1 electron on the surface. Happens to be in the 2s orbital. Okay, where's that last electron? It's on the surface. So your Lewis dot structure is the chemical symbol with 1 dot. So I can put a dot here on the right, or I can put it on the left, or I can put it up above, or I can put it down below. Those are all legal Lewis dot structures. When we start connecting atoms to make molecules, that'll help guide you as to where you want your electrons placed, above, below, left, and right. So we'll get into that in future units. Let's go way over here. We said, well, let's choose one of the halogens. Keep picking on them. I like the halides. Let's do bromine. Bromine, its chemical symbol is Br, and it's in column 7. So there's 7 dots around bromine. Okay, so the Lewis dot structure might be Br with 7 dots. It is going to be Br with 7 dots. What am I saying? You get to decide where you want to start putting dots. You want them on the right, left, up above, down below. All are legal. I'm going to pick up above. My second one can't pair up, though. Right? So we're following Hund's rule. Spray them out, equal orbitals, that old jazz. So maybe I'll put one here, put one here, put one there. There, 4 dots, 4 electrons. Bromine has 7, though. Now I must pair up. And you decide how you want to pair them up. And again, when we start making molecules, connecting atoms to atoms, I'll give you some guidelines as to where you might want to pair up and where you might want to avoid pairing up. But really, it doesn't matter at this point. So I'm going to pair these 2 up and these 2 up. There we go. I got 7 dots. And my unpaired electron is down here on the bottom. But the unpaired electron could have ended up on top. I know, it looks like I'm pairing them up immediately. I shouldn't. Should put them up like that. Follow Hund's rule. Okay, and let's have a dot on an unpaired electron on the left. And what's my last possibility? It could have been on the right. There we go. You pick one, whatever works. What about the noble gases? Turns out there's 2 legal ones. So let's grab xenon, element 54. How many valence electrons on xenon? It's in column 8. So there's 8 dots. Xenon has chemical symbol Xe, has 8 dots, so 1, 2, 3, 4. Now pair them up. 5, 6, 7, 8, and I'm done. So it looks like xenon only has one possibility, 8 dots. That's not true. This is a legal Lewis dot structure. What are you doing, Dennis? This is following 2 definitions for the valence electrons. We've been talking about the valence electrons on the surface. They are in the outermost shell. So xenon in the outermost shell, the last shell being filled, has 8 electrons. Ooh, and 8 electrons did fill that shell. That's why xenon is noble, a noble gas. But we could also define valence electrons as the first unfilled shell, right? So if we go back to lithium and ask about its electron configuration, lithium, this way. We would say, okay, lithium, your element, there you are, you're element 3. Where are the 3 electrons? Well, the first electron's like hydrogen, row 1, s block. Second electron pairs up, it's the 1s electron. Third electron now starts filling the second row, second shell. I'm gonna need 8 electrons to fill up the second shell. So the first unfilled shell of lithium, first unfilled shell is the second shell. There's only 1 electron in that second shell, that's why it has 1 dot. Bromine is found in the 4th row. We're filling the 4th shell. There was 2 electrons that were 4s. Then there were the 10 3d electrons. Wait, that's not 4th shell. Once you get to element 31, you're in the 4th row, p block, and you put in 5 electrons. Oops. So bromine, we had the 2s, that's 4. We're in the 4th row, 4s, and then we're actually starting to fill the 4p, and there's 3 p's, and we put in 1, then 2, and then 1, 2, 3, 4, 5. So the 4th shell has 7 electrons in it, and that's where the 7 dots. Xenon, we're filling the 5th shell. We had 2 of the S. We have 6 of the P. We have the shell 5 is now full with 8 electrons. But what if I ask, where's the first unfilled shell? After Xenon fills its 5th shell, 5th shell's full, so now it's time to start filling the 6th one. That one's not filled yet. There are no electrons there. So that's why the Lewis dot structure for xenon can be just the chemical symbol by itself, saying, hey, the first unfilled shell doesn't have any electrons in it. Okay, that's going to be useful. So these two are legal structures. Awesome. Hey, we've come to the end of the topics for this video. One last note. Some of the homework questions in the future may use the letter Z to represent the atomic number. I don't use that very often. I'm not going to use it on exams. So for example, a homework question might read, what's the name of the element with Z equals 79? And I want you to be able to say, oh, Z, that's that funky symbol for atomic number. Atomic number, what's that again? Number of protons. So which element has 79 protons? Oh, it's right over here. That's a gold atom. Ooh. So the name is gold. So just be aware that if you see a homework problem specifying a Z number, it's talking about the number of protons. The atomic. All right, that's plenty for now. Take care.